Alright, so the purpose of this video, well, this video is a sequel to the video which hopefully you just watched about logarithm laws. This is part 2 of that. So, I want to establish the so-called change of basis formula. So, let's start leading up to it. So, this is the reason that the change of basis formula holds. Is really just how do there's this fact about how logarithms interact with exponentials. The fact that if you have the log base b of a to the x, you will always get something of the form x times the log base b of a. Oh, but check this out. So this is just like one of the log laws that we just established. But if you look at this again, you'll see that that's an equation in logarithmic form. I see the log base b of a thing is equal to a thing. So I can rewrite this in exponential form, and if I do that, what do I get? Well, I'm taking the log away from the left-hand side, so I'll have an a to the x on the left-hand side is equal to b raised to the power x times the log base b of a. And that is a compelling and important result. So that says if you can, so let's just state it. So you can describe any exponential you like in terms of your favorite exponential. If your favorite exponential is the exponential with base 10, you can describe every exponential in terms of exponentiation base 10 at the cost of introducing a logarithm. A to the x is equal to b raised to the x times the log base b of a. So if you want to express 2 to the x in terms of an exponential with base 3, well, 2 to the x is equal to 3 to the x times the log base 3 of 2. Very nice. And that's all it is. You can write any exponential in terms of any other. You can write pi to the x in terms of the exponential with base e. Pi to the x is the same thing as e to the x multiplied by, I'm about to sneeze, you have to pause. Excuse me. Pi to the x is the same thing as e to the x times the log base e of pi, also known as e to the x times the ln of pi. And in fact, this isn't something that's terribly relevant to you in this class, but this is how a calculator will understand any exponential. A calculator has a very good technique coming from the so-called Taylor series to compute e to the x for anything that you would want to put in the exponent. It has a Taylor series that's very good for computing the natural log. You put those two things together, a calculator is now very good at computing e to the x times the natural log of any input. So it's good at computing any exponential. So let's go back up to looking at this. So I know that 2 to the x is equal to 3 to the x multiplied by the log base 3 of 2 from above. So let's do a quick log base 3 of 2 is about 6.3, so that means 2 to the x is approximately the same as 3 to the x multiplied by 0.63. Oh, well then I know how to graph 3 to the x times a number. So what does this conclude? This means the graph of 2 to the x is the same as the graph of 3 to the x but with all x values divided by 0.63. Approximately 0.63, really the log base 3 of 2. So what does that mean? That means the graph of 2 to the x should look the same as the graph 3 to the x, but all the x values will be divided by 0.63, so all the x values will get bigger by some factor. So that should mean the graph of 2 to the x is the same as the graph of 3 to the x horizontally stretched. And no one's here to correct my spelling of stretch, but I guess I should do my best. Stretch. That still seems wrong. Is it like, okay, horizontally stretched. And let's just see that that actually looks reasonable. There's this x value. If I stretch it horizontally, it'll go out there. Yeah, it looks like this is walking out. All the x values on 2 to the x are the same as the x values on 3 to the x, but a little bit bigger. So the other change of basis formula that I want to mention is the change of basis formula for logarithms. And the premise, the reason that this will be true, will also have to do with how exponentials and logarithms interact. And well, here, let's see exactly that. Let's start with this. So logs and exponentials undo each other. That's the whole point of logs. So that means a to the log base a of x is always equal to x. And there's nothing deep there. That's just saying exponentiation and logarithms are inverses to each other. But something fancy will happen if I apply log base b to both sides of this. I'll get the log base b of a to the log base a of x is equal to the log base b of x. And that might seem like a totally nonsensical thing, but something interesting is about to happen. I can simplify the left-hand side using logarithm laws. I see an exponential there. So what'll I get? I'll see log base a of x. I can pull that out of the exponential and write it down as a multiple, log base a of x, multiplied by the log base b of a is equal to the log base b of x. And there's no reason for you to care about this just yet, but there's about to be. What if you wanted to take this and solve it for the log base a of x? Well, if you wanted to solve that for the log base a of x, you would just divide this over to the other side. So let's do exactly that. That'll give me log base a of x is equal to the log base b of x divided by the log base b of a. And this is an important formula, and I'm about to write it again. The log base a of x for any base a can be written as the log base b of x divided by the log base b of a. So what that means is if you know any one log function, you know them all. You can express any log function in terms of any other. You can express log base 3 of x in terms of log base 10 of x using this formula. Log base 3 of x is equal to the log base 10 of x divided by the log base 10 of 3. And for some of you, this would be very relevant. Those of you who use handheld calculators, your handheld calculator might only walk in log base 10. It secretly doesn't. It probably walks in log base 10 and can also walk over the natural log. The point is, if you know how to make your calculator take one logarithm, you can get your calculator to take any logarithm by using this fact. Then again, this is now an online class, So I don't think I have any way of limiting what technology you have access to. So you can use things like Wolfram Alpha, which would be perfectly happy to allow for any logarithm input that you want. Of course, what Wolfram Alpha will do is it will use this fact. So let's use that. Okay, so writing this down, the log base 3 of x is the same as the log base 10 of x divided by the log base 10 of 3. And just as in the previous example, I'm going to want to estimate the log base 10 of 3 just to write down something that's a little bit more explicit looking in order to understand the graph below. So I'm going to pause for a second. Well, first I'll show you that what I'm going to do while paused is pull this up and do a computation. Okay, and we're back. So there's the computation. The log base 10 of 3 is approximately 0.5. And that's good enough for me. It's approximately 0.5. So this is about log base 10 of x divided by 0.5. And we are being approximate, but we can simplify at this point. So log base 3 of x looks like it's about 2 times the log base 10 of x. It's only approximate, but that's okay. So let's just write down that conclusion right here. So the log base 3 of x is about 2 times the log base 10 of x. What does that mean? That means, in terms of graphs, so that means the log base 3 of x, the y values on log base 3 of x will be double the y values on the log base 10 of x. Y values on the graph of, sorry, I didn't say graph, of log base 3 of x are about double the y values on log base 10 of x. And let's just take that fact and interpret it. So right here, I'm telling you that one of these is the log base 3 of x, the other one is the log base 10 of x. I know that the log base 3 of x is the one that has y values that are doubled the other one. So it looks like this one has smaller y values. If you go from there to there, it looks like you're doubling. So then it must be that this one is the log base 10 of x, while this one is the log base 3 of x. Very good. The next two things are just like neat tricks. So you'll notice that at no point in anything that I've done have I had a variable in the base of a logarithm. And on the one hand, like it's more natural to have a fixed base and have the parameter inside of the logarithm changing. That comes up more in applications. But there's another good reason. It doesn't need to be. So let's take this and use the change of basis formula and see what we get. So let's try to express the log base x of b by using the change of basis formula. So apparently the log base x of b in log b will be, so I'm going to color code a little bit. This will be red, this will be blue. So the change of basis formula, I'm going to translate it into base b, says that I should get the log base b of the thing that was originally inside of the parentheses divided by the log base b of the thing that was originally in the base. Oh, but let's simplify that a little bit. Log base b of b is 1 divided by log base b of x. Oh, so when you see a variable inside of the base of the logarithm, basically just means you're going to take a reciprocal. So there's no need to ever think about the situation of there being a variable in the base of a logarithm, because you can get the variable out of the base by instead doing some division because of the change of basis formula. The one last trick that I want to illustrate really is just kind of a trick. Let's think about what the log base 2 of 3 times the log base 3 of 2 is. And the way that I'll do this is I'll use the change of basis formula to express everything in terms of a single log, a single base. And this will be, I think, kind of a neat trick. So let's do that. Express everything in terms of a single base. And maybe I'll even suppress the base. So I won't even, it doesn't matter which base I pick, so I won't pick a base. You can in your head. So the log base 2 of 3, by the change of basis formula, that should be the log of 3 divided by the log of 2. Sorry, let's write down what this is. Log base 2 of 3 times the log base 3 of 2 is equal to, log base 2 of 3 is right there. Now let's compute that, times the log base 3 of 2. That'll be the log of 2 divided by the log of 3. There's even the correspondence, which bit becomes which. Oh, but I see some cancellation that happens. Log of 3, those will cancel. Log of 2, those will cancel. And so I'm left with 1. Nice. So the log base 2 of 3 times the log base 3 of 2 is just 1. And in fact, there was nothing special about 2 and 3. I think that's just always true. So there's some illustrations about some things you can do with the change of basis formula for logarithms. I'll go ahead and call this lecture done.